Rebecca, and take it away when you're ready.
Oh. Can you all see my screen?
Yes.
Well, thanks for the long introduction that I believe I gave you, but I appreciate that. So today I'm going to be talking about magnetic field diagnostics for the chromosphere of the sun. And I know there's several non-solar folks in the audience. I'm going to start with a very brief and superficial introduction to the sun, its magnetism, and why we care about measuring them, which is essentially what I do. So relatively speaking, the sun is a magnetically quiet object when you compare it to other known objects in the universe. But this relatively small amount of magnetism can have large impacts on the heliosphere and therefore on the Earth. And this movie shows the passage of sunspots across the sun's disk as the sun rotates. Sunspots have been observed for many centuries now, but back in the times of, let's say, Galileo, people didn't really know what they were, what the nature was. It wasn't until just over a century ago that George Ellery Hale hypothesized that sunspots must contain magnetic fields. So he set up an experiment to go about detecting these magnetic fields using the theory that Peter Zeeman had developed just a decade earlier on the interaction between radiation and the magnetism. And Hale was successful. He was able to detect magnetic fields inside a sunspot. And now we know that sunspots are just places where very strong concentrations of magnetic field pierce through the sun's surface and intersect the surface, leaving this dark imprint on the surface. Magnetic fields, the magnetic fields in sunspots make them dark because the very, very strong nature of these magnetic fields inhibits convection and therefore the propagation of energy to the surface. This makes the sunspots colder than their surroundings and therefore darker. But the magnetism of the sun is not really confined to magnetic fields only. It actually appears virtually everywhere. This video on the left shows a magnetogram of a small patch of quiet sun taken by the IMAX instrument on board of Sunrise. The label quiet sun was given to areas of the sun that were outside of active regions and sunspots when scientists thought that there were no magnetic fields outside of these areas. But the sun is really not quiet. It's full of magnetism everywhere at all spatial scales and at all temporal scales that we can imagine. This video on the left, as I said, is a magnetogram. A magnetogram is just a image of the magnetic field at the sun's surface, and it's derived from the measurements of polarization of the light that the sun emits through, typically, the Zeeman Effect. So magnetic fields appear at all possible spatial and temporal scales, and they challenge the detection ability of our telescopes and our instruments. But magnetic fields in the sun are important because they are able to store large amounts of energy as they are twisted and they're moved around by the convective motions at the sun's surface. And they're also able to trap large volumes of material in these twisted and often unstable configurations, as the one that you see in here. This is a video of a filament eruption taken by the Solar Dynamics Observatory. So when these configurations are driven to a state of imbalance, the magnetic fields can suddenly rearrange, reconnect, releasing all the mass and the energy that was stored inside them and producing powerful space weather events. So just to summarize why magnetic fields are important, they play a very important role in the structure, the dynamics, and the energetics of the sun's atmosphere. They have the capability to store, to transport, and deposit energy amongst different layers and different parts of the sun. And they're fundamentally at the root cause of space weather events. The magnetic fields of the sun connect the inside of the sun to its atmosphere and also draw pathways through the entire solar system through which these space weather events can travel. So in order to be able to better characterize and forecast space weather, we need to be able to quantify the states and the evolution of the sun's magnetic fields throughout its entire atmosphere. And this brings me to the topic of my talk today. I'm going to talk about different techniques used to characterize or measure the magnetic fields in the sun's chromosphere. The chromosphere of the sun is a thin crust of the sun's atmosphere that sits a few hundred kilometers above the solar surface, which here is depicted by this wedge. Is in between the dynamically driven photosphere of the sun and the magnetically dominated corona, which is an even more tenuous layer that extends many solar radii out into space. The chromosphere is very interesting because it harbors the key to quantifying the amount of magnetic free energy that can then be made available to solar eruptions. So with this, this brings me to the outline of my talk. I've already sort of gone over a brief introduction about the sun's magnetic fields. Now comes the second part of my introduction. It's about spectropolarimetry, how we measure the intensity of the polarization of light that comes from the sun, and how we do that, how we can use that in order to infer information about the magnetism in the sun's atmosphere. And then I'll talk about the two specific subtopics of this colloquium. There are two diagnostic techniques that I'm going to be assessing their validity and the range of validity when applied to a specific spectral line that forms in the chromosphere of the sun, and how well do these techniques infer the magnetic conditions in the sun's chromosphere. And then at the very end, I'm just going to give a brief glimpse into the future and how we are now using machine learning techniques to approach the spectral line inversion problem. So another basic introduction, and maybe for people that are used to radiative transfer, this is very superficial, but bear with me. So light is not only characterized by its intensity as a function of frequency, but also by its state of polarization. Light is an electromagnetic wave. It's transverse in nature, and that means that the electric field and magnetic field that describe it oscillate in the plane perpendicular to the direction in which it propagates. If the electric field vector oscillates along a line, we say that the light is linearly polarized. If the tip of the electric field vector describes a circle in time, such as in what you can see in the animated GIF there, we say that the light is circularly polarized. And if the electric field vector describes a random path in this plane, we say that the light is unpolarized. Of course, you can have a superposition of all three. The Stokes parameters, I, Q, U, and V, typically, are a set of four quantities that fully characterize the polarization of the light. Stokes I represents the intensity or the total energy in the light. Stokes Q and Stokes U characterize the linear polarization and its direction. And Stokes V quantifies the circular polarization and its handedness. So when we take the light from the sun and we spread it out into all of its different colors, what we get is an image of the sun's spectrum. And the sun's spectrum is littered with thousands and thousands of black lines that we call spectral lines. These are places where light of very specific colors is missing. And these are just the fingerprints of the atoms and the molecules that compose the sun's atmosphere. So spectral line happens when a photon is absorbed or emitted as an electron undergoes a transition from one bound energy level to another bound energy level inside an atom. This figure on the top represents a model of the energy levels inside the hydrogen atom and the transitions that its electron could possibly undergo. And below, you have the resulting emergent spectrum from this hydrogen atom. Now, each atom and each molecule in the sun's atmosphere imprints a very, very specific pattern of lines on the spectrum. So now let me go to the place where I really want to go, which is how do we infer magnetic fields from the spectrum of the sun? Now, imagine that this cartoon is depicting two bound energy levels inside an atom, and this is a transition that an electron can undertake inside them. These energy levels are denoted by the quantum number J, U for up and L for low. And in general, these energy levels are degenerate. This means that there are multiple magnetic sublevels inside them sitting at exactly the same energy. In the presence of a magnetic field, these magnetic sublevels split, breaking that degeneracy. And this leads to a wavelength shift between the pi and the sigma components of the spectral line. So what was originally one spectral line turns into a multiplet with several components that slightly shifted in wavelength with respect to each other. The pi component of the spectral line is just defined as that satisfies that delta M equals 0. M is the magnetic quantum number. And the sigma component satisfy delta M equals plus or minus 1. In the electric dipole approximation, the pi component of the spectral line absorbs or emits light that is linearly polarized along the direction of the magnetic field, whilst the sigma components of the transition absorb or emit light that is circularly polarized in the plane perpendicular to the direction of this magnetic field. So this is what we call the Zeeman Effect. And in the Zeeman Effect, the splitting of these energy levels is proportional to the magnetic field strength. And the polarization signatures that emerge from this effect tells us about the orientation of the magnetic field vector in space. If the magnetic field is 0, if there is no magnetic field, then there is no wavelength split or shift between the pi and the sigma components of the spectral line. And then there are no emergent polarization signatures. This is true as long as the number of pi and sigma components transitions per unit volume and time is identical. And this is true provided that the populations of the magnetic sublevels for a given energy level are identical. And this is what this cartoon is trying to depict, actually. Each box in this cartoon represents a magnetic sublevel, and the little circles inside the boxes represent the populations, the atomic populations that exist in each one of those energy states. So what happens when this is not the case, when these magnetic sublevels are unevenly populated? Well, in that case, what you'll have is that there will be an imbalance between the number of pi and sigma transitions per unit volume and time, and this will cause an emergent polarization signature without the need to invoke a wavelength shift between these components. This is without the presence of the magnetic field. There are mechanisms that are able to create this population imbalance, which we refer to as atomic level polarization. And this in itself creates emergent polarization signatures in the radiation. Now, in the sun, the most common mechanism that leads to atomic level polarization is the anisotropic illumination of the atoms that are responsible for the spectral line. And this typically happens in the higher layers of the sun's atmosphere, in the chromosphere and the corona. So when you have an atom that's sitting deep in the photosphere on the sun at the base of the atmosphere, is receiving illumination from all sides almost equally in an isotropic way. But as you go to higher and higher layers of the atmosphere, it becomes more and more transparent. And then those atoms sitting at higher layers experience a different amount of radiation coming from below than coming from the sides. So it's this anisotropic illumination that is able to create this imbalance in the populations of the magnetic sublevels, and therefore emergent polarization signatures in the spectrum. These polarization signatures generated in this way are usually referred to as scattering polarization. So let me show you a little bit more visually what this means in the spectrum or in a spectral line. Let's say that you have a case where no atomic level polarization is allowed. All the populations are going to stay equal. So polarization can only be generated by the Zeeman effect, in other words. But the magnetic field is 0. So in the case of the Zeeman effect only, and the magnetic field being 0, we know that there cannot be any emergent polarization signatures. At the bottom, I'm showing you the synthesis of a spectral line of calcium-2. This is the intensity as a function of wavelength, and then Stokes Q and Stokes U as a function of wavelength. And what I'm not showing here is Stokes V, which is irrelevant for what I'm going to be showing next. But in any case, Stokes Q, U, and V for the Zeeman effect with the magnetic field of 0 Gauss are exactly 0. Now let's allow a mechanism that can introduce atomic level polarization. The magnetic field is still 0. what happens? These are the emergent polarization signatures. Now, as opposed to before, we have a Stokes Q signal. This is a scattering polarization signal. There is no Zeeman effect introducing polarization in the spectral line. So this sets the framework to explain briefly what the Hanle effect is. The Hanle effect is the modification of the atomic level polarization of these population imbalances due to the presence of a magnetic field. So if I now, in this scenario, introduce a small magnetic field, let's say of 1 Gauss, and this magnetic field has to be actually inclined with respect to the axis of symmetry of the radiation, this magnetic field has the ability to modify the population imbalance amongst these magnetic sublevels, and therefore will modify the emergent polarization signatures with respect to the zero field case. So now in this case, the emergent polarization signatures are the pink ones. And what you see is that Stokes Q has changed sign and Stokes U has appeared, which was not there before. And if you were just curious what the Zeeman signatures due to a magnetic field of 1 Gauss would be without scattering polarization, don't know whether you can actually see it, but they produce this faint green line that essentially sits at 0 polarization. It's not exactly 0, but it's so small in comparison to the scattering polarization signatures and their modification due to the Hanle effect that you can't see them. So this is what this is telling you, is that this Hanle effect is a good diagnostic technique for very, very weak magnetic fields in the sun, where the Zeeman effect cannot produce measurable signatures. So now that I've spoken a little bit about different mechanisms that can introduce polarization in spectral lines, let me give you an overview of how we go about interpreting measurements of the intensity and polarization of light. So I'm going to introduce you to the concepts of forward modeling of spectral lines and spectral line inversions. If we know the physical state of the sun's atmosphere, if we know its temperature, its density, its magnetic field, etc., we in general know, how to solve the radiative transfer to calculate the intensity and polarization properties of the light that this atmosphere would emit. But of course, in general, we want to solve the opposite problem, right? We have a set of observations of the sun, of the intensity and the polarization of light inside a spectral line, and you want to do the inverse mapping in order to obtain information about the physical state, the physical conditions in the sun's atmosphere that generated these observations. So let's look at these two processes more in detail. First, the forward problem. Now, under certain physical scenarios, one can make a series of approximations that greatly simplify the forward problem. But this, unfortunately, is not the case in the chromosphere. In order to properly model the spectral line that forms in the chromosphere of the sun, one has to reckon with the fact that its radiative transfer needs to be solved in the full-blown non-LTE regime. Non-LTE stands for non-local thermodynamical equilibrium. And also that in many cases, the spectral line polarization will be due to a combination of scattering processes and the joint actions of the Zeeman and the Hanle effect that I introduced earlier. Now, solving the radiative transfer problem in non-LTE means the following. You need to solve simultaneously and self-consistently the radiative transfer equation and the statistical equilibrium equations. The radiative transfer tells you how light is absorbed, emitted, and scattered as it travels through the sun's atmosphere, whilst the statistical equilibrium tells you about the composition of the sun's atmosphere, how many atoms and molecules in each possible energy state there are. The problem is that you have to solve, the solution of the radiative transfer is the input for the statistical equilibrium and vice versa. So you need to solve these sets of equations in an iterative manner over and over again until they converge to a solution, and then you can calculate the synthetic spectra that the model atmosphere would generate. This is, needless to say, computationally intensive. When one adds to this the computation of polarization signatures due to scattering processes and their modification via the Hanle effect and so on and so forth, it becomes a really, really computationally intensive problem. It becomes a supercomputer-worthy computation problem. The traditional way in which we do the spectral line inversion, what we have done for a long time, entails yet another layer of iterations on top of this already complex forward model. And this is because traditional spectral line inversion codes use a non-linear least squares approach to minimize the difference between the synthetic spectra and the observations. So they're trying to make the synthetic spectra match our observations, and for that they need to do the forward modeling many, many, many times. So again, when you can imagine that if the forward modeling is so computationally expensive, the inverse problem, including all of these physical processes, is completely prohibitive, at least in the traditional way that it's always been done. This means that we either need to find alternative, much faster ways to solve this inverse problem, or use other diagnostic techniques that do not require this kind of computation, but still deliver solid inferences of the vector magnetic field in the sun's atmosphere. So now I'm going to actually go to the topic of my talk. I'm going to be assessing two different methods to infer the magnetic field in the sun's atmosphere. But first, I want to introduce you to the spectral line that I'll be using to assess these two different inferences. It's the spectral line of calcium-2 at 8542 angstroms. Calcium-2 is just a singly ionized calcium atom. This is one of the most common spectral line diagnostics used for diagnostics of the solar chromosphere. And this is because its line core, the center of the line, forms in the chromosphere of the sun, whilst the spectral line wings form very, very low in the mid-photosphere of the sun. It is a magnetically sensitive line, so that means that its polarization signatures are sensitive both to the Zeeman and the Hanle effects, and it is accessible from ground-based telescopes because it sits in the near-infrared part of the wavelength part of the spectrum. Now, another thing that makes it popular is that there are certain simplifying modeling assumptions that one can use to make it a little bit simpler to model this line compared to other chromospheric lines. However, scattering polarization dominates the linear polarization signatures of this line in quiet sun areas. This is in places where the magnetic fields are typically weak and particularly close to the limb. Scattering polarization is very geometry dependent, so the polarization signatures due to scattering processes tend to become larger and larger as we observe closer and closer to the limb of the sun. This makes properly modeling this calcium line, if we want to account for all of these effects, it's very, very computationally expensive, and there are no spectral line inversion codes to date that are able to properly model the spectral line polarization accounting for these processes, for the degeneration polarization due to scattering and its modification via the Hanle effect. So the first subtopic that I wanted to talk about is the weak field approximation applied to the spectral line of calcium. The weak field approximation is a conceptually rather simple but computationally very, very affordable method for doing inferences of the strength and the orientation of the magnetic field from observations of the intensity of the polarization of spectral lines. And it relies on the Zeeman splitting being smaller, a lot smaller than the Doppler width of the spectral line. If you remember that I said earlier, the Zeeman splitting is proportional to the magnetic field strength. And the Doppler width of the spectral line is just the natural width that that line would have under the same thermodynamical conditions in the absence of a magnetic field. In practical terms, what it means is that the magnetic field needs to be in a range of strengths where the Zeeman splitting that it causes is not noticeable within the width of the spectral line. If you were to look at an intensity spectrum, you would not see the splitting. Fortunately, chromospheric spectral lines are pretty broad, making the range of application of such an approximation a little easier. So under this approximation, one can apply a perturbative scheme to the polarized radiative transfer equation and arrive at a much simpler set of equations that connect the linear and the circular polarization to derivatives of the intensity with respect to wavelength. So the first equation on the top connects Stokes V, the circular polarization, to the derivative of Stokes I with respect to wavelength. Both of these are observables through a factor that depends on a constant, particular to each spectral line, and on the line of sight component of the magnetic field. So this is the geometry that I'm going to be referring to. Let's say this is the vector magnetic field in the sun's atmosphere. This here is its projection along the line of sight, along the z-axis. And we denote this as BLos, line of sight. The line of sight is just the line that connects the observer, you, me, to the point in the sun that we are observing. The second equation connects the linear polarization, the total linear polarization, to the derivative of the intensity with respect to wavelength. And it does this through a proportionality factor that depends on the transverse component of the magnetic field. If you go back to that geometry drawing, this is the projection of the magnetic field onto the transverse plane, transverse to the line of sight. And the third quantity that characterizes the vector magnetic field in this reference system would be the azimuth angle. The azimuth angle in this perpendicular plane, in this transverse plane. And the relationship says that the tangent of 2 times this azimuth angle equals the relationship, or the ratio between U and Q, both observables. These equations are true provided that the magnetic field is weak enough to meet this weak field approximation, and they were all derived assuming that there were no velocity gradients and no gradients in the magnetic field in the sun's atmosphere. That, of course, is very ideal. So I wanted to assess the range of validity of this weak field approximation applied to this spectral line of calcium-2 formed in the chromosphere of the sun. So the way I did it was to synthesize the intensity and the polarization of this line in known model atmospheres with known values of the magnetic field, and then interpreted these synthetic polarization signatures using the weak field approximation. Then I could compare these inferences to the magnetic field in the model to assess how good the approximation was. I used the synthesis package of the spectral line inversion code MICOR to compute the synthetic spectra. This is a non-LTE one-dimensional radiative transfer code, operates in plane parallel geometry. The polarization signatures in this code are due to the Zeeman Effect only. And for my base model atmosphere, I used a semi-empirical model of the sun, FAL-C. This is a very standard semi-empirical model, the one-dimensional model that describes the sun's atmosphere as a function of height. Then I added to this model ad hoc vector magnetic fields of different strengths, different orientations, and different vertical gradients. All right, so first I wanted to evaluate the validity of the weak field approximation to extract information about the line of sight component of the magnetic field. And this is through this equation that relates Stokes V to the derivative of Stokes I with respect to wavelength. So I generated 48 different model atmospheres based on this FAL-C model, but I changed the magnetic fields. I included vertical magnetic fields with different strengths and different gradients that varied from 0 to 750 Gauss per unit of log tau. Now, in radiative transfer, we don't usually refer to height as geometrical height in kilometers. Oftentimes, you see this other different representation as a function of optical depth, which is a much more natural unit for distance in radiative transfer. The logarithm of the optical depth of 5,000 angstroms is a standard in solar physics to refer to heights. And in this scale, the base of the sun, the photosphere, the base of the atmosphere of the sun sits at 0, log tau 0, whilst as you go to higher and higher layers in the atmosphere, the logarithm of the optical depth becomes more and more negative. So this is higher layers, this is lower layers in the sun's atmosphere. And this panel is just showing one of the model magnetic fields. It has a linear gradient as a function of height in the atmosphere. From each one of my models, I generated the Stokes spectra. This shows Stokes I and Stokes V as a function of wavelength. And then I applied the weak field approximation in the core of the line and the wings of the line separately. So in the core, it's represented by green and the wings by orange. I did this with the hopes of extracting meaningful values for the magnetic field in the photosphere and the chromosphere separately. So when I applied the weak field approximation in those two wavelength ranges, I obtained a value for the core of the line, BC, and a value for the wings, BW, and then I mapped these values down to, map them into the magnetic field of the model to obtain the heights in that model atmosphere that these values were probing. I did this for all 48 different models, and I calculated the average tau core and the average tau wing from all of the inferences. Then in order to assess how good the weak field approximation for the line of sight component of the field was, I plotted the weak field approximation inferences for the wing of the spectral line in this case against the model value evaluated at the average height obtained from the inferences for the wing, for the wings of the spectral line. And what you can see is that the inferences fall exactly on top of the module values. The black line just shows the 1-to-1 ratio, independently of the magnetic field strength and the steepness of the magnetic field gradient in the model. I did the same for the inferences from the core of the spectral line. So these are the weak field approximation inferences on the y-axis, and the model magnetic field evaluated at log tau minus 5.4. This was the average log tau for the core of the line. And what I get is that the inferences map rather well the magnetic field of the model up to about 1,000 to 1,200 Gauss, depending on how good you want your assessment to be. After that, or beyond that, the inference deviates by more than 10% with respect to the model value. So what we managed to prove here is that we can apply the weak field approximation in the core and the wings of the spectral line separately and actually get good inferences for the chromospheric and the photospheric magnetic fields separately. Now, in the presence of velocity gradients, spectral lines develop asymmetries. And even though the weak field approximation formulas were derived, assuming that there were no velocity gradients, I still wanted to evaluate whether this weak field approximation would break down in the presence of a moderate velocity gradient like the one shown now in red in this model as a function of height. So I generated the spectra in the presence of velocity gradients in the same 48 models. And now you can see that both Stokes I and Stokes V have developed asymmetries. I still applied the weak field approximation in the core and the wings of the spectral line separately. I obtained the corresponding values for the magnetic field, and I traced them back to the model atmosphere to obtain the average height probed by the weak field approximation applied in these wavelength ranges. To get a sense of how good the results were, this is the same plot as earlier, but in the case of velocity gradients, and what you can see is that the results are qualitatively and almost quantitatively the same, meaning that in the presence of moderate velocity gradients, the weak field approximation is still valid and one can still apply it. It does break down when you have velocity discontinuities, larger velocity discontinuities or shocks at certain heights in the atmosphere. So next I wanted to evaluate the weak field approximation for the transverse component of the magnetic field. And this is the equation that rules that, or one of the forms of the equation that rules that. So it connects the linear polarization to a derivative of the intensity with respect to wavelength. And now this little W, subindex W here, is telling us that we cannot apply this equation at the spectral line core, at the very center of the spectral line, because it creates a singularity. So we have to apply it a little bit away from the very core of the line. Because I wanted this to be a diagnostic for the chromospheric magnetic field, I still applied it in something that I call the core wing boundary of the spectral line. So avoiding the singularity that would happen at the very core of the spectral line, but also avoiding the outer wings of the spectral line that I know are mostly photospheric. So they would bring information from lower down, photosphere of the sun. I created 70 different model atmospheres with uniform magnetic fields, different strengths, and different inclinations with respect to the line of sight, between 10 and 90 degrees. 90 degrees corresponds to a magnetic field that's perpendicular to the line of sight. And these were the solutions that I found. So this figure on the right shows the inferred transverse components of the magnetic field from the weak field approximation as a function of the magnetic field in the model. And each one of the little diamonds is an inference. The colors just denote the different inclination angles in the model atmosphere. And what you can see is that they mostly actually agree with, or closely agree to the truth, which is the black dashed line, and certainly are, for the most part, within 10% of the solution, represented by the dotted lines. Only in the case of a transverse magnetic field at 90 degrees does the solution, the inference, deviate more than 10% from a solution. And lastly, I wanted to apply the weak field approximation to extract or infer the magnetic field azimuth in the plane of the sky. And this is the equation that rules that. I'm just going to go straight to the results without boring you with details, but what I found was that the difference between the inference and the model azimuth in degrees was actually rather large. This is a difference of up to 20 degrees in some cases. And this is unacceptable from the point of view of trying to infer a good valid azimuth for the magnetic field from the weak field approximation. But why is this happening? So if you go back to the equation, it says that a tangent of 2 times the azimuth angle equals the ratio of u over q. So it's expecting this ratio to be constant. And if you were to plot u against q, you will see that they're actually not constant in general. They actually deviate a lot from a constant value. So and u in the wings of the spectral line is represented by the solid line. It's actually pretty linear, and it's linear, and in fact, it coincides with the tangent of 2 times the azimuth angle. But once you get into the core of the spectral line, represented by these dashed lines, that ratio really deviates from that constant. And this happens because something called the magneto-optical effects. As light travels through the sun's atmosphere, the electric field vector changes in phase. So effectively, you have a crosstalk between the different polarization states of the light. The polarization changes from one state to another, changes from Q to U, and from the linear polarization to Stokes V. These are called magneto-optical effects. And this results in this ratio changing as a function of height. So these are my conclusions for the weak field approximation assessment. It is a reliable method to at least qualitatively, if not quantitatively, estimate the line of sight components and the transverse components of the magnetic field in a wide range of field strengths, up to 1,000 Gauss, or maybe even a little bit more. Even though I didn't show it here, this weak field approximation does break down in the very weak field regime, where the polarization signatures, at least the linear polarization signatures, are dominated by scattering processes and the Hanle effect. So in that context, below a magnetic field of 100 Gauss or up to 200, depending on the observing geometry, this weak field approximation does break down. But for larger field strengths, it's actually valid to up to 1,000 to 100 Gauss. So the next question that I asked myself was, how much better or worse do standard traditional non-LTE spectral line inversion codes do when interpreting the intensity and in particular the polarization of this calcium 28542 line? This is work in progress that I'm doing with my collaborators at the IEC in Spain and Stockholm University in Sweden. And the way I went about this project was similar to the case of the weak field approximation. So I synthesized calcium 8542 intensity and polarization spectra in known model atmospheres and with known values of the magnetic field, and then I inverted them or interpreted them with the spectral line inversion code STIC. So in this case, I did the synthesis with the Hanle RT radiative transfer code. This was developed by Roberto Cassini and Tanosu del Pino Aleman, and it's a non-LTE, one-dimensional radiative transfer code for complex polarized atoms. It operates in plane parallel geometry. It is able to model spectral line radiation in the partial frequency redistribution regime. And importantly for this particular project, it is able to model the polarization of the spectral lines due to scattering processes as well as the joint actions of the Zeeman and the Hanle effects. In a similar fashion as before, I used my base model atmosphere. I used the false C semi-empirical model, and I added ad hoc vector magnetic fields, uniform vector magnetic fields of various strengths to it. The magnetic fields were always tangent to the sun's surface, and we computed the emergent spectra for different observing geometries. 3 of these observing geometries are depicted below. The one on the left is the case for an observing geometry where we're looking at the center of the disk of the sun. This is always represented by a mu angle, the cosine of the heliocentric angle. So for this center observation, it's mu equals 1. The magnetic field is represented by this black arrow. These are 2 observing geometries as we go progressively towards the limb. This is the most extreme limb geometry that we generated. It's 84 degrees with respect to the disk center observation. You haven't, so you can see them. The reason we did this was because the scattering polarization signatures increase in amplitude as one observes closer and closer to the limb. This is a geometric effect that has an impact on the range of magnetic field strengths where the Zeeman signals are dominating over the scattering polarization signatures. So close to the limb, the scattering polarization will dominate over the Zeeman signatures in a larger range of field strengths. After synthesizing the spectra, we inverted them with the spectral line inversion code STIC, which was developed by Jaime de la Cruz Rodriguez and his collaborators. This is a non-LTE spectral line inversion code based on a one-dimensional radiative transfer code RH, developed by Han Uitenberg. It also is in plane parallel geometry. It is also able to model partial frequency redistribution regime and spectral lines, but the polarization signatures that it generates are only due to the Zeeman effect. And this is precisely the thing that I really wanted to quantify is how well does this inversion code that only generates polarization due to the Zeeman effect, how well does it interpret these synthetic polarization signatures from Hanle RT that contain the full physics of polarization generated by scattering and this modification via the Hanle effect. For each one of these model atmospheres, we actually generated 2 sets of spectra. One where we did the full calculation with scattering polarization, and the other one where scattering polarization was turned off, and the polarization was due only to the Zeeman effect. And you have 2 examples here at the bottom. On the left, Stokes I, Q, U, and V for a magnetic field of 100 Gauss, and the 2 calculations, the scattering polarization in red, the Zeeman-only case in blue. These are the synthetic spectra calculated with Hanle RT. But you can see that if you look at Stokes Q in particular, there's a big difference. between the full calculation and the Zeeman-only case. And this is because we're still in a regime of field strengths where the scattering polarization signal and the Zeeman signal are comparable in magnitude. For the case of 500 Gauss, the difference between the linear polarization signatures from both calculations is very, very small. And this is because we're now in a regime of field strengths where the Zeeman signals dominate. All right, so now let me just go to the results. First, I'm going to show you the results for the spectral line inversions for the viewing angle of disk center for mu equal 1. This is because, as I said earlier, the signatures due to scattering polarization increase as we go to higher and higher viewing angles. The mu equals 1 case is the one where we're going to have smaller scattering polarization signatures. So what I'm showing you here is the best fit. Now the blue line is the spectrum generated by a STIC inversion code. It's the best fit that the STIC inversion code was able to obtain for the Hanle synthetic spectra. At the top, you have the case of the full calculation, Stokes I and Stokes Q as a function of wavelength. And at the bottom, you have the Zeeman-only case. Now, if we start looking at the Zeeman-only case at the bottom, you can see that the STIC inversion code is able to fit very well both the intensity and the polarization of the line. And you can see the blue line fits really well over the red dots that represent the Hanle synthesis. But if you look at the case of the full calculation at the top, even though it's not surprisingly the intensity is still very well fitted, the inversion code is not able to fit the linear polarization in the spectral line. It's able to more or less try to attempt to fit the wings and maybe the amplitude of the polarization signal, but it is definitely not able to fit the shape of the spectral line. And this is because the STIC inversion code does not contain the relevant physics in order to be able to model this polarization signal. Let's look at the results. By the way, this is just for one case of 100 Gauss. So let's look at the results for the case of mu equals 1 in terms of what is the inferred magnetic field that STIC is able to obtain and how does that compare to the magnetic field in the model. And this is what I'm showing here. On the y-axis, the inferences from the inversion code. On the x-axis, the magnetic field in the model. At the top, you have the case of the full calculation. And at the bottom, you have the Zeeman-only calculation. So what you can, again, the many different things that you can extract from this plot. But even though the spectral line inversion code is not able to super accurately in all cases fit the magnetic field of the model, it does a really good job, in fact, at inferring the magnetic field strength. But the other thing that you can see is that there is no statistically significant difference between the inversions of the spectral lines with the full calculation and the inversions of the spectral lines in the Zeeman-only case. And that is a big takeaway. For the most part, the polarization signatures in most of the range of field strengths are mostly dominated by the Zeeman effect, and the inversion code doesn't care that there's scattering polarization signatures. It does not try to interpret them and is not misled by them. Now let's look at the solutions for the spectral line inversions for all the other viewing angles. Now, in these plots, these plots all represent or show the inferred magnetic field minus magnetic field of the model in percentage points. So 0 would be a perfect inference from the STIC code of the magnetic field of the model. Each one of the viewing angles is represented by a colored circle, and the left shows the results for the Zeeman-only case, whilst the right shows the results for the full calculation. Now, again, as earlier, for the most part, there is no significant difference between the job that the inversion code is able to do on the Zeeman-only signatures and on this full calculation signatures with scattering and polarization, except for very low field strengths, where you can see that the inferences are off by a substantial amount. So let me show you why this is happening. These are colored plots are showing the linear polarization, the Stokes-Q signals obtained from Hanle T in the case of the full calculation for a case of a magnetic field of 0 Gauss. So these are essentially scattering polarization signatures. There is no Zeeman signal in them. And you can see that as you go to viewing angles closer and closer to the limb, from left to right, the amplitude of these scattering polarization signatures becomes larger and larger, as expected. These Stokes-Q signals are going to mislead the spectral line inversion code, who is going to be trying to fit them, assuming that they are caused by the Zeeman effect. So this is what the black line is showing in each one of the panels. The black line is the STIC's best attempt at fitting each one of these spectral lines in each one of these cases. This, of course, leads to magnetic field inferences that are non-zero. In fact, the inferences go from 0 in the case on the very left side to 10 Gauss, up to 110 Gauss in the worst case, where it's trying to sort of fit this scattering polarization signature of an observation really close to the limb. This happens because the STIC only cares about minimizing the difference between the synthetic and the observed spectra. It doesn't really care what physics goes into the observations, of course. So essentially, this leads to an overestimate of the magnetic field strength in cases where the signals are totally generated, exclusively generated by scattering processes. So these are my conclusions. STIC is remarkably, rather surprisingly for me at least, rather good at inferring the transverse component of the magnetic field. It does the solutions are equally accurate regardless of whether the polarization signatures have scattering contribution or Zeeman-only, as long as this Zeeman contribution is comparable, if not dominant, to the scattering one. And only in scenarios where the field strength is very low, below 100 Gauss, and the viewing angle is close to the limb, where scattering polarization really dominates. Only in these cases, the inversion will severely overestimate the magnetic field strength. And lastly, just 2 more minutes, allow me to introduce you to a project that started last year. This was a project to develop a quick look spectral line inversion code for chromospheric spectral lines using machine learning techniques with the goal of actually really speeding up this inverse mapping process. This work is currently being done under the framework of NCAR's reinvestment projects, and these are the team members. Lippi is a postdoc that joined us in May of 2020. She started working full-time on this project, and she's mainly leading the project. And it's a shame you guys have not met her, but she's been working at HAO for more than half a year now. So this is the way we're going about this project. We are using state-of-the-art MHD simulations, magnetohydrodynamical simulations of the quiet sun from the Muram code developed partly by Matthias Rempel to obtain a lot of different realizations, realistic realizations of the sun's atmosphere, of the sun's physical state. Then we're collecting all these different realizations into a database of physical states, and we are computing the corresponding Stokes spectra using the Hanle code. So now we have 2 databases, one of physical states and one of spectra, with many, many, many different realizations of each. And we are designing and training neural networks that can do the inverse mapping between the database of Stokes spectra and the database of physical states. This is work in progress. I will not report anything right here. I'm sure that in a few months, Lippi will be able to give you a colloquium on this topic. And with that, thank you very much. I welcome any questions that you may have.
Thank you very much, Rebecca. Yes, so if anyone has questions, there is a raise hand feature on the bottom right of your screen, or else feel free to type it in the chat. Becky, do you have a question?
Yeah, I got a question. Great talk, Rebecca. It's interesting that STIC, you know, for the disk center case, came up with the right answer, even though it wasn't really able to fit the profile very well when you showed the fit that you showed. So, but it came up with the right field nonetheless. And I don't know if I can be encouraged by that, because is anyone going to accept that in an analysis? I mean, let's say you do a disk center observation and you come up with a lot of magnetic fields, and you say, well, this study shows that everything's going to be accurate, but none of my profiles fit.
No, and I'm not trying to say that either. I was trying to establish the range of validity in which we can actually really accept the results that an inversion code like this would produce. And I am fully aware that below maybe the range of 100 Gauss, or maybe a little bit more depending on the observing angle, there is a potential for the inversion code to just be completely misled by the polarization signatures. But yeah, you always need to be aware of that. And when you do inversions like this, it is, I guess you can't do it when you do large numbers of inversions, but you do really want to look at the quality of the fits to ensure that you're actually modeling the spectral line properly too. So that was visible in the inversion. I'm not able to model the spectral line, but just by modeling more or less the amplitude of the line in the Zeeman regime, it was able to come up with the right field strength, more or less.
Yeah, if I can add to the comment, because I was thinking exactly about the same thing, and there is a simple heuristic explanation for that. At the beginning, Rebecca has presented, right, how the Zeeman effect is a polarization generating phenomenon. If you don't have Zeeman effect in an LTE line, you end up not producing any polarization. Whereas instead, the Hanle effect is a modification of an existing signal of scattering polarization. In the case that Rebecca showed in a 1D atmosphere, right at the center, because of the symmetry, that's the situation where the Hanle, both the Hanle effect and the Zeeman effect become purely generative of polarization. So the Hanle effect is no longer something that takes an existing polarization signal and modifies and destroys the last. It is actually generated the same way as the Zeeman effect. Things will be different if you start moving away from the 1D approximation, right? If you start considering a realistic cube of an atmosphere, like a neuron simulation right at the center, and you start taking into consideration that the symmetry is broken, even this looking exactly extended by horizontal anisotropes, then you start creating a zero field polarization signal. And the Zeeman effect and the Hanle effect will start behaving differently again, just like it happens away from the center. I don't know if it makes sense. It will be a ramble, but in some sense, the fact that the Hanle effect was able to map closely what the Zeeman effect was doing, it's almost an accident of the fact that at this center you really have, in a 1D atmosphere, just a generation of polarization with both effects.
Yeah, you can refer to the plots that I showed in one of the last slides, where the inversion code was trying to fit the polarization away from the center, and it did a much worse job.
Okay, Han, do you want to ask?
Yes, yeah. So since the 8542 and 8498 have different scattering properties, I'm not exactly sure how much different they are, but I think they are different. Would looking at both lines at the same time maybe allow you to disambiguate a little bit more?
Probably, but I'm not doing any Hanle inferences. Neither the weak field approximation nor the STIC inversion code know anything about the physics of the Hanle effect. Yeah, from the Hanle diagnostics point of view, I mostly defer to Roberto, but the answer is probably yes. No.
Okay. If there are no further questions, then thanks again, Rebecca.
Oh, yeah, thank you.